This is for class 12, and these are the important for both concept and for both your competition or for your board exam See, one the important thing here is, see, you consider a sphere and charge q is distributed over this surface, and this is a conducting sphere. See, conducting sphere. Here two cases are there. One is conducting sphere, and another is the non-conducting sphere. Two cases: conducting sphere and non-conducting sphere. So here you see that this is a sphere and a charge q is distributed over here, and here this is of radius r, say radius r. So electric field inside the sphere is 0. Electric field inside the sphere is 0. Electric field inside the sphere is 0. See here. But your potential, what is your potential? It is the negative integral of EdL. Say from infinity to r, we bring it from infinity. Negative integral. So here this will be, your potential on the surface will be minus infinity to r E is your q by 4 pi epsilon naught r square dr. So this will be equal to minus infinity to r. So here this will be here. It will be minus q by 4 pi epsilon naught r to the power of minus 2 dr. So this will be minus q by 4 pi epsilon naught infinity to r to the power of minus 2 plus 1 by minus 2 plus 1 infinity to r. So what you are going to get? This will be minus, so minus q by 4 pi epsilon naught. So this will be minus 1 by r, so infinity to r. So this will be upper limit, so this comes out to be q by 4 pi epsilon naught r. So here you see that what is your potential? Potential is q by 4 pi epsilon naught. But the potential inside is not 0. Here the potential is same as the potential inside, about everywhere inside the sphere is the same as that on the surface. So no work is done to move a charge from Q to this to the center or anywhere inside the sphere. So see the important fact is that what is the important fact? That is the potential energy inside the sphere is 0. Electric field inside the sphere is 0. But the potential, that is V, potential on the surface and inside the sphere is the same. But your potential on the surface and potential inside the sphere is the same. That means it is an equipotential surface. It becomes an equipotential. Potential is same. So no work is done when we move the charge from the surface to inside the sphere. If we move the charge, there is no work done. No work. So what I want to tell you, no work. The important point which you must remember here is that the electric field inside the sphere is zero. The electric field is outside this sphere. The electric field inside this sphere is zero. But you see that the potential on the surface is this, and the inside is also the same. So here, to move the charge from Q to Q inside the sphere, no work is done. That means the potential is same. That means it is an equipotential surface. It becomes an equipotential surface. So see the difference. Here inside your electric field is zero, but there is a potential. That is the potential of this. Electric field is zero, but there is a potential inside the sphere, and the potential outside the sphere is equal to the potential inside the sphere. So see the important fact that you must remember. This is the important fact. So this is for a conducting sphere. Now if we go for a non-conducting sphere, then you see what happens. You go for a non-conducting sphere. What is going to happen? Let us see. Now let us consider non-conducting sphere. So here in non-conducting sphere, you see what happens. That is of radius r, Q charge is here. So let us find what will be the electric field at a distance r. What will be the electric field at a distance r, means r is less than r, and what will be the potential at a distance r from the center. So for this you have to go for charge density, volume charge density. You have to go for volume charge density. That will be equal to rho. That will be equal to Q by 4 by 3 pi r cube. You have to go for. Now what is the charge enclosed in this sphere? So the charge enclosed, Q enclosed will be rho into Gaussian volume. This is the Gaussian volume. So this will be equal to rho. Gaussian volume is 4 by 3 pi r cube, and your density is Q by 4 by 3 pi r cube into 4 by 3 pi r cube. So this comes out to be here Q r cube by r cube. This is your Q enclosed. So now we are going to apply the Gauss law. So according to Gauss law, what will happen according to Gauss law? What will happen? That is cyclic integral of E dA, that will be equal to Q enclosed by epsilon naught. So here this is the sphere, so this will be cyclic integral of dA. So this Q enclosed is this, so this will be Q r cube by r cube, and E, that is 4 pi r square. So this will be equal to epsilon naught. So this will be equal to q r cube by 4 pi r square epsilon naught r cube. So this comes out to be q r by 4 pi epsilon naught r cube. This is the so this is equal to q. So that means if it is a non-conducting sphere, we have electric field inside the sphere. But if it is a conducting sphere, remember, if it is a conducting sphere, then electric field inside the sphere is 0. But if it is a non-conducting sphere, then there is an electric field that is equal to this. And again, you can find the potential. Your potential will be, you can find your potential that will be from infinity to r, that is q by 4 pi epsilon naught r square dr, and plus r to r 2 by 4 pi epsilon naught r square dr. So you can find the potential by the help of this formula, same. So what is the difference here you find? If it is a non-conducting sphere, then there is an electric field inside the sphere, and electric field is this, and also we have potential this. This is small. And if you calculate this, you will get the potential. So see the difference. The difference is that when it is a conducting sphere, remember, when it is a conducting sphere, remember, that is the your electric field on the surface. There is an electric field on the surface of the sphere, and there is an electric field outside the surface, because the charge is considered as a point charge. But the electric field inside the sphere is 0. But there is a potential. That is, the potential on the surface is equal to the potential inside the surface. That means it acts as an equipotential surface. So no work is done. See the difference. But in case of a conducting sphere, you have a non-conducting sphere, you have electric field inside the sphere as well as you have potential inside the sphere. So see, this is the difference what is happening here, and why I want to tell you that it will help you to solve the problems, and it will help you the main concept. If it is a conducting sphere, remember your electric field inside the sphere will be 0 if q charge is distributed on the surface, but your potential on the surface is the same as the potential inside the sphere. But in case of non-conducting sphere, what do you find? That is, there is electric field inside the sphere as well as you have potential inside the sphere. Here, because it is the negative, this will be minus and minus, because potential, it is the potential, it is what? It is the negative integral of your potential, negative integral of it is the negative integral of E here. So here this will be minus and minus. If you calculate it, you will get the potential. Now let me go for another concept. Let me go for another concept, that is with transformer. Another concept with transformer. Here you see that the formula is Vs by Vp is equal to Ns by Np, and your Ip by Is is equal to Vs by Vp is equal to Ns by Np. So let me clarify it. That is, Vs is the potential on the secondary coil and Vp is the potential on the primary coil. Ns is the number of turns in the secondary coil. Np is the number of turns in the primary coil. Ip is the current in the primary coil. Is is the current in the secondary coil. And so from here you see one thing, one important thing here you see that here, that is Vs by Vp, Vs by Vp is equal to Ns by Np. So Vs is equal to Ns by Np into Vp. Here you see. That means here you see this thing. Again you see a relation here, that is Ip by Is is equal to Vs by Vp. So Is by Ip is equal to Vp by Vs. So Is is equal to Vp by Vs into Ip. So here you see. Here you see one thing like that. This is Vs. If Ns, if number Ns is greater than Np, Ns is greater than Np, Ns is greater than Np, that means your Vs is greater than Vp, that means your Vs is greater than Vp. So it is a step up transformer. Step up transformer. It is a step up transformer. Here you see. If Ns is greater than Np, and so Vs will be greater than Vp, so it is a step up transformer. Again, you see here that if Ns is less than Np, so your Vs will be less than Vp. So this is a step down. This is a step down transformer. This is a step down transformer. So here again you see that means if Vs is greater than Vp, Vs is greater than Vp. So here this is a step up transformer, but your Is is less than Ip. And when your Vs is less than Vp, Vs is less than Vp, then your Is is greater than Ip. So the important point I want to tell you here is that in step up transformer, no doubt the output voltage is greater than the input voltage, that means it is a step up transformer, but your current in the secondary coil is less than the current in the primary coil, and in the primary output. Similar in step down transformer, here you see that your Vs is less than Vp, but your current in the secondary coil is greater than the current in the primary coil. So such type of things can only happen. Remember, you may be confused. There a confusion must be arise in you. That is your Vs is greater than Vp. So how Is is less than Ip? Because if you apply Ohm's law as V is proportional to I, that means as potential increases, your current must increase. But V is proportional to R, it is Ohm's law, it is applicable to purely resistive circuit. Remember, it is applicable to purely resistive. It is purely resistive circuit. It is applicable to purely resistive circuit. But here this is induction. But here this is induction. But here this is induction. This is the difference. So this, do not confuse, because that will be applicable only in purely resistive circuit, but here induction is taking place. Well, since induction is taking place, so it does not obey your Ohm's law. It does not obey your Ohm's law here. So here, when Vs is greater than, that means output potential is greater than the input potential. That means it is a step-up transformer. Your current in the secondary is less than the current in the primary. And similarly, in step-down transformer, your output potential is less than the input potential, but your current in the secondary is greater than the current in the primary. So do not confuse with the purely resistive circuit, because this is an induction, this is an inductive circuit. Here there is a coil taking place, and so because there is it is on the theory of electromagnetic induction. This is on the theory of electromagnetic induction. So this can't be applicable with the Ohm's law. So do not confuse with this. So this is the important fact I want to tell you, that do not hear this induction is taking place. So such type of concepts I want to clear it for you. Now again, another concept I want to tell you. So another concept about this, you have studied that is F is equal to Q V cross. So here you see that all these three are mutually perpendicular to each other. Here you see that this is the most important fact. Here you see that all these three are mutually perpendicular to each other. That means this is your magnetic field that is into the plane of the paper. This is your magnetic field into the plane of the paper, and a charge with velocity v perpendicular to the magnetic field. A charge with velocity v is moving perpendicular to the magnetic field. Then a force will act inward. This force F will act inward, and this force is also the centripetal force. This is the centripetal force. This is the centripetal force, and this centripetal force, this is the centripetal force. So here you see that this centripetal force, this is the centripetal force, and this centripetal force, that is mv square by r, and this is equal to qvb. This is equal to qvb. So here there is a centripetal force, that means there is a centripetal acceleration. There is also a centripetal acceleration. So here you see that because this is force, here there is a centripetal acceleration. So here you see that if F is perpendicular to B, because they are mutually perpendicular, so here again acceleration is also perpendicular to B. So your A dot B will be 0. See how the things are being related. How the things are being related. So mv square by r, this is the centripetal force. That means centripetal force, there is a centripetal acceleration. So the centripetal acceleration is, since F is perpendicular to B, so your centripetal acceleration is also perpendicular to B. So A dot B will be 0. Now again, here you see, in case of a galvanometer, here you see, in case of a galvanometer, what happens? That is, if a galvanometer is means galvanometer reading is 1 microampere. A galvanometer can read 1 micro. Full scale deflection will be 1 micrometer, that is equal to 1 into 10 to the power of minus 6 ampere. 10 to the power of minus 6 ampere. So here, if you want to measure a current of 10 amperes, if you want to measure a current of 10 amperes. So what, and we know that to measure current, we connect this in series. Galvanometer is connected in series. And a galvanometer, it has a high resistance. Galvanometer, it has a high resistance. So since the galvanometer has a high resistance, what will happen? That means you won't get the actual current flowing through the circuit because of this high resistance. You won't get the actual current flowing through this circuit. So what it is done, a parallel resistance, a parallel shunt resistance, a very low resistance, a very low resistance is fitted parallel to the galvanometer, so that the maximum current flows through this circuit, that means the flow of the current is not affected. See, the flow of the current is not affected. So because galvanometer is a high resistance, to measure the current, it is always connected in series. So if we connect in series, we won't be able to get the actual flow of current. So to get the actual flow of current, a shunt of low resistance is attached, fixed parallel to the galvanometer, so that the maximum current flows through this shunt resistance. And when the maximum current flows through the shunt resistance, that means your galvanometer will give the full deflection. And you will be able, you can say that your 10 ampere current is flowing through. That means you can say that a 10 ampere current is flowing through. Now the same is the case with if you use this as a voltmeter. So this galvanometer, a resistance of high resistance in series must be connected to the galvanometer, because to measure potential difference we connect this in parallel. So when that means this voltage is, let's say, V. So if we connect a high resistance, so let this potential be V1 and this is Vg, and so your V1 plus Vg will be equal to V. So here, if the galvanometer gives the full deflection, that means this is the potential difference across these 2 points. This is the potential difference across the 2 points. Now again, because here the resistance is this, what is this high resistance? That means this potential V, suppose let us take 230 volt, and your galvanometer potential difference is maximum, say 1 volt, say, then this V1 will be round about 229 volt. It will be 229 volt. The resistance will break here, this 229 volt. So this plus this will be 230 volt. I am just giving you an example. So here, if it is the full, here you will get the full deflection. That is, there is 230 potential differences between the 2 points A and B. So to convert this galvanometer to a voltmeter, a resistance of high resistance is connected in series with the galvanometer, so that the maximum potential drops here and the galvanometer is able to give the full deflection. And when the galvanometer gives the full deflection, that means it is 232. So here this is another concept. So now again here you see that again here you see one thing that one thing again here you will see. Suppose now if you you can if these concepts are clear with you, if these concepts are, you can now able to solve any problem concerning with transformer, concerning with conducting sphere, non-conducting sphere, concerning with when a charge is moving in a magnetic field and the force, because F, Q, V, they F, V, B, they are perpendicular to each other. Again, in case of this galvanometer as an emitter or a galvanometer as a voltmeter, that means in galvanometer as an emitter. So what will be the shunt resistance? Suppose what will be the shunt resistance? Suppose the question is like this. We know that the galvanometer it can measure 1 microampere. So if you want to measure 10 ampere current and your resistance of the galvanometer is given to you, so what will be your shunt resistance? So you can calculate it. Similarly is the case with the voltmeter. When this acts as a what we call galvanometer acts as a voltmeter. Similarly, you can do such type of problems. That is, suppose this is a non-conducting sphere and a charge. Here, this is a charge Q. It is moving with some velocity and has entered somewhere here. It has entered somewhere here. So, what is your final velocity? Suppose this is a such type of problem. This is a non-conducting sphere. Suppose this is a non-conducting sphere, and a charge Q, and here there is a charge Q. So a charge Q, it is moving with some velocity and has entered to this distance. This is the center. So what will be the velocity, your final velocity here? So such type of in this type of questions, you have to use the law of conservation of energy. Law of conservation of energy. You have to use the law of conservation of energy. Law of conservation of energy. That means law of conservation of energy. That is initial your potential energy initial plus kinetic energy initial, and this is equal to potential energy final and kinetic energy final. Your kinetic energy final here will be 0 because here it stops here, and here it stops here, and you have initially what is the potential here, the potential here at B. So potential here at B, suppose this is at a distance, suppose something, say let R, something at R. So what is the potential at this? Here your potential moving with charge, this will be something Q by 4 pi epsilon naught R. Here this will be your potential, and here your initially your kinetic energy will be half mv square. So your final potential, your final, because it is a non-conducting sphere, so your kinetic energy will be 0. Your final potential will be something like this, infinity to R Q by 4 pi epsilon naught R dr minus to R Q by 4 pi epsilon naught R dr. So and this r may be r by 2, this r may be r by 2 or something what it is given to you. From this you can calculate the final velocity there. So here you see, if you know this concept, if it is clear with you, then you can solve this problem easily.